Good afternoon once again. This time around, we're going to describe the chem photosynthetic pathway. This pathway was first discovered in succulent plants of the family Crassulaceae family. And because of that, the name of this pathway was coined behind the family of the plants in which it was first discovered. That family is Crassulaceae. So the pathway was called Crassulacean acid metabolism. Crassulacean acid metabolism, abbreviated simple as chem. Today, we simply call it the chem pathway. The chem pathway is not very different from the C4 pathway. They have got a lot of similarities. The similarities are as follows. In the chem pathway, the enzyme PEP carboxylase is involved, just like in the C4 photosynthetic pathway. So, in the chem pathway, when carbon dioxide gets into the leaf, it is converted into bicarbonate, as you can see here. This is also the situation in the C4 photosynthetic pathway. That bicarbonate that has got one carbon will interact with phosphoenol pyruvate, abbreviated as PEP, a 3-carbon compound. Just like in the C4 pathway, the first compound to be formed has got 4 carbons. And that compound is called oxaloacetic acid, or simply abbreviated as OAA. So you can see the stomata hub opening, CO2 coming into the leaf, that CO2 being converted into bicarbonate after interacting with some water there, forming a bicarbonate which has got a charge. The next step, that bicarbonate combines with PEP to form OAA, which has got 4 carbons. That OAA, just like in C4 plants, is going to be converted into another 4-carbon compound called malate. At that conversion, it's accelerated, catalyzed by an enzyme called NAD malate dehydrogenase. That's the name of the enzyme there, right? Take note of the following. This is happening during the night in chem plants. In C4 plants, this will be happening during the day. So that's the difference between chem photosynthesis and C4 photosynthesis. From there, this malate which is formed, it's stored in the vacuole of the mesovir cells. Whereas in C4 plants, that malate which is formed is delivered to the vascular bundle sheath cells. There's no such here in the chem plant. The malate that is formed during the night, by the way, is delivered into the vacuole of the same mesovir cells and stored there. So this will keep on happening. Malates will keep on being formed, stored in the vacuole, and then come daylight, this vacuole will be so full of the malate molecules or malic acid. Hence, the word Crassulacean acid. The acid name is coming from the malic acids that are stored inside the vacuole, that accumulate in the vacuole over the night. What happens then? During the day, you can see during the night the stomata are open. CO2 is coming in, or air is coming in. Come during the day, we shift, we come to this slide. During the day, the stomata gets closed. No more CO2 is coming in, no more air is coming in. The stomatas are shut during the day. Then what happens? So it means from early in the morning, the stomata of this plant will be closed. Then the next thing is that malate which was stored in the vacuole of the mesoville cells will be delivered from the vacuole into the chloroplast of the mesoville cells. Malate is formed during the night and stored in the vacuole. During the day, malate is delivered from the vacuole, taken out of the vacuole, and delivered into the chloroplast of the mesoville cells. Vascular bundle sheath cells are not involved here. So this movement of malate from the vacuole into the chloroplast is happening during the day, at the time where no more CO2 is getting into the leaf because the stomata are now closed. So this malate, just like in the C4 plants, is going to be decarboxylated, which means it is broken down into carbon dioxide and a pyruvate. You can see this pyruvate here is a 3-carbon compound. Then when this malate is broken, the carbon dioxide is released, just like the carbon dioxide also being released in the vascular bundle sheath cells in C4 plants. The released carbon dioxide enters the Calvin cycle. It enters the Calvin cycle. And the Calvin cycle will result in the formation of starch. It will result in the formation of glucose molecules, which the chem plant can use for other purposes. It can form sucrose, it can form starch, they can form cellulose, and so on and so on. So some of this starch, we go back here, some of this starch that is formed during the night will be converted into pyruvate. Some of this starch will be broken to regenerate the pyruvate. The pyruvate that is formed during the night when malate is broken down will also be converted into starch. This is happening during the day. But come during the night, starch will be burned. Starch is going to be burned during respiration and it will release pyruvate. So that means starch will first be broken down into glucose molecules, and these individual glucose molecules will be burned down further and they will release this pyruvate. Some of these pyruvate molecules that are released as a result of starch being broken down, the pyruvate is going to be delivered from the chloroplast into the cytosol of the mesoville cells. And from there, that pyruvate is going to be phosphorylated, converted into phosphoenol pyruvate, PEP. This is done through the enzyme called pyruvate phosphate dikinase. There is the name of the enzyme there. Pyruvate phosphate dikinase. And therefore, this will result in the regeneration of the PEP. So that is basically what happens in the chem pathway. Part of the carbon dioxide fixation takes place in the night. So in these plants, what takes place in the mesophyll cells in C4 plants during the day? In chem plants, that part takes place during the night within the mesophyll cells. The common issue is here also during the night, everything is taking place within the mesophyll cells. In C4 plants, that malate, same time during the day, is delivered into the vascular bundle sheath cells. Here in the chem plants, that malate is not delivered to any vascular bundle sheath cells during the night, but it is stored in the vacuole during the night. Early in the morning, the vacuole will be so full of these malate molecules, a lot of acid early in the morning. As the day progresses, that acid becomes less and less and less and less because malate is taken out of the vacuole, delivered into the chloroplast, broken down, and each and every time each malate is broken down, no acid is there anymore. If you break malic acid, there is no more malic acid. So from the morning till about the evening, early in the morning, there will be so much malic acid in the vacuole, but by the evening, there will be no malic acid anymore because those malic acids, each and every one of them, would have been moved out of the vacuole into the chloroplast, broken down to release CO2 and to form pyruvate. CO2 goes into the Calvin cycle to form glucose molecules that will also be used to form starch and so on and so on. Later in the night, that starch, which has been formed during the day, some of it is going to be bent down during respiration to form pyruvate molecules within the chloroplast. Pyruvate will be delivered out of the chloroplast into the cytosol of the mesophyll cells and later used to regenerate the PEP. That is what happens in the chem pathway. Thank you. Good afternoon, ladies and gentlemen. I'm back once again. What you see on this slide, remember the last slide that I sent you dealt with C4 photosynthesis and the ability of this pathway or the strategy used in this pathway by the plants to minimize the process of photorespiration. What you see on this slide, here you can see this green teff. That's basically a typical lawn. Here you can see a crabgrass, these black-like weeds that are growing amongst the lawn. This is in springtime when the temperature is about 20 degrees Celsius, and the bottom structure shows you the situation when the temperature is 30 degrees, that is during summer. The crabgrass is a C4 plant, whereas this green lawn is a C3 turf grass. You can see that during springtime, when the temperature is low, there is a lot of green there, and very few crabgrasses are growing. What is the reason for this? The reason is this one. When the temperature is low, under low temperature conditions, the process of photorespiration becomes very minimal, almost negligible, but it is still there, but it is very minimal. And therefore, when the process of photorespiration is very minimal, the plants who suffers from that process tends to be at an advantageous position. Therefore, they can grow better under these low temperature conditions. Since photorespiration, which minimizes their growth, it's very low, they can take advantage of low photorespiration, increase their photosynthesis, thereby increasing their growth. They are able to outcompete the crabgrass, which is a C4 plant. Remember, the C4 photosynthetic pathway, it's long and it is expensive. 2 enzymes are used in that pathway. A lot of enzymes are actually used in that pathway, not only 2, more than 2 enzymes. I think 4 or 5 enzymes are used in that pathway. Enzymes are proteins. They must be made by the plant. So that pathway is long and that pathway is expensive in terms of resources that are needed for that pathway to take place. And the advantage is that that pathway is able to minimize photorespiration. So in a situation in which photorespiration is not so much of a problem, that pathway is no longer that beneficial because it was designed mostly to deal with photorespiration. And when photorespiration is not there, that becomes some kind of a wasted pathway. A lot of energy invested and without so much benefits for the plant. A plant will not easily just change its mode of photosynthesis just because it is hot or it is cold. So a C3 plant will stay being a C3 plant and a C4 plant will stay being a C4 plant. So under low temperature conditions, there is more photosynthesis, less photorespiration, and therefore C3 plants, because their photosynthesis does not waste a lot of energy, can grow better and outcompete C4 plants. That's why you see too much green and very few crab grasses there, or we can say, let's call them weeds. The bottom part, the same situation. Now in summer. In summer it is hot and photorespiration is high. Therefore, C4 plants that can minimize photorespiration are at an advantageous situation here. They can minimize photorespiration. Temperatures are high. Photorespiration is very high. Therefore, those plants that have got a pathway that is designed in such a way that photorespiration can be minimized will now benefit from that kind of a photosynthetic pathway as opposed to the C3 plants. C3 plants under high temperature conditions will be subjected to so much photorespiration and very little photosynthesis, such that their growth is going to be minimized, their productivity is going to be minimized, whilst the photosynthesis of C4 plants, it's increased. That of the C3 plants will be decreased. And therefore, it goes without saying that C3 plants, C4 plants under these high temperature conditions, summertime, will grow faster, will grow better, will photosynthesize better. And you then start to see a lot of weeds mushrooming all over the turf lawn here. So if this condition, if you are not weeding out these C4 weeds, with no time, they would have covered the whole lawn there. And if the situation is allowed to continue as is, these weeds, the whole garden can just be weeds, replace all the lawn turf there, the C3 lawn grass, replaced by these weeds, this crab grass, that is a C4 plant. So this is basically the situation. The situation is that in situations where temperatures are high, and normally it is also a bit dry under those conditions, C4 plants are favored under those conditions as compared to C3 plants. On the other hand, in situations where temperatures are low, 20 degrees and below, C3 plants are favored as compared to C4 plants. So this basically means the mode of photosynthesis, plants that photosynthesize through the C3 pathway, called the C3 plants, will tend to be dominant in areas that have got low temperatures, cool areas. Whereas plants that photosynthesize through the C4 pathway will tend to be dominant in areas that are hot, areas that have got high temperature conditions. So you can see the mode of photosynthesis of the plant can determine its distribution. It can determine where that plant is likely to be found growing in high numbers. So here you can see a clear relationship between photosynthesis of the plant and the ecology. Very interesting. The physiology of the plant playing a role in the ecological aspect in the life of a plant. This is very interesting to note, and I want you to understand that. So when you go out there in the field, the distribution of the plants, patterns of distribution in terms of C3, C4 plants, obviously will be determined by the photosynthetic mode that these particular plants are using, will play a role in the distribution of those plants. So I hope you understood this difference, this aspect between C3 and C4 plants in terms of how their survival is linked with photorespiration, the absence or presence there of it. In the next slide, I'll be dealing with another photosynthetic pathway called the CHEM pathway. So just watch out for the next slide. I hope you enjoyed this clip. Thank you very much.